Hey team, we will have a look at now at component 2 of the Unit 1 practice exam on functions, relations and polynomials. So it's written here, component 2 at the base of the left pillar, so based on the prior component where there was a length of slide and we had some pillars supporting it, but at the base of the left pillar, Molly is designing a metal shield to cover the pump that pushes water to the top of the slide. She has a rectangular aluminium sheet of length 400 centimeters and width 240 centimeters. The cover is made by cutting square corners and folding the flaps down where X will be the area of each square cut. So there's a couple key things there, and I've highlighted, underlined them, but I'm going to highlight them. We're cutting out some square corners out of the sheet, and where X will be the area of the square cut out. Okay, so let's draw a picture, which is what we're asked to do. Molly has asked you to find what is the range of possible volumes that could be made, the maximal possible volume of the cover, what the final dimensions are, and how much aluminium would be wasted as a percentage of the original area of the sheet if made to maximize volume. Okay, so let's jump in and draw a basic picture and identify what's going on here. So we have 200, no, let's go the other way. We have 400 centimeters across and we have 240 centimeters vertically. They are our dimensions of the original aluminium sheet. From here, what happens is we cut square corners out. So take off a square out of there, take off a square out of there, take off a square out of there, take off a square out of there. From there, that allows you to then fold along that line there, along that line there, along that line there. So we end up three-dimensionally. If we fold along those blue bits, okay, we have a front edge that folds down, and then the edge, and then same on the back side. Okay, that happens. So we end up with this box. Okay, with the red bits are cut out, and the square that cuts out ends up being those two lines. Fold them down; they'll end up joining together. Okay, those two edges will end up touching each other when we fold the flaps down. So that's what's happening. So we want to diagram the sheet with the corners cut out, labeling all dimensions. Okay, so we've labeled our 240, we've labeled our 400, but let's actually think about what's this shape's going to look like once we cut it out. Well, we end up more this. And again, you would draw this with a ruler, but I don't have a ruler. Actually, can I? Now I say that, can I hold shift and get straight lines? Yes, I can. Lovely. There we go. So we end up with this shape. So as we said, all the way across is 400. And importantly, we were told that the area of one of these square cutouts, of each square cutout, is X. Okay? So if we think about how do we get an area here of X? Well, the two widths, okay, if area is equal to X, and that is also equal to, because it's a squared, it will be length squared, the length on the side will be equal to the square root of X. So that's the important connection we need to make, is that the length of each side to give an area of square X is that those two bits are square root X. So we can label that as square root X, 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 square root X. Okay, so we have all of those. So that's fine. We still need to label the actual far sides and top and bottom. So what does that mean? Well, if it's 400 all the way across, and we know there is square root X, and we know there is square root X, that leaves us that this must be 400 minus 2 square root X. And that's the same there and there. Both of those will be 400 minus 2 root X. We can also apply the same principle to the sides, if we know that bit there is square root x and we know that bit there is square root x, well, if the whole thing was 240, that means that the remaining bit will be 240 minus 2 square root x. Let's clean this up a bit. Okay, so now we have a diagram with all our dimensions. Okay. We know that, let's put 2 blue lines. Okay, those two sides are both 240 minus square root x. And we can apply that to, let's use brown across here. Okay, I'm going to draw that in brown across there. So now we can actually start to visualize what's happening to our box that we've made. It's an opened bottom box essentially. If we fold our flaps actually down, okay, this is the top, okay, that's the front, and that will be the side. Okay, top here, front, and then our side in over there. So that's the opened bottom box. You can imagine placing over the top of a pump to seal it in. So what is so we've done draw the diagram to shape the corners, find the function to express the volume V centimeters cubed of the box in terms of x. Well, volume of any box is going to be length times width times by height. And we've figured out that going across here, that is 400 minus 2 root x. The height of the box is root x, and the width of the side is 240 minus 2 root x. So there is our length, width, and height. So we get 400 minus 2 root x, 240 minus 2 root x, and root x. Okay. Now we can simplify this, and this is where it is handy to use our calculator, and we can clear everything we've had from before. Since we're doing a new problem, let's clear everything and all our variables. And math 1. Let's use g this time. G of x is equal to, actually we won't even do that. We're going to jump to an action, and we want to transform a function. We want to expand it. So we want to expand, and in our first one we have 400 minus 2 square root x. Second set of brackets is 240 minus 2 root x, and our last bracket is just square root x. And we don't need to technically put that last square root in brackets, but we will. And then we need to, because our command, technically, if we go back here, the expand command starts with a bracket, so we want to close, tell it everything inside that is what we're expanding, and we get this. And let's get out of decimal mode, run it again. There we go, there's our function. We get 4x to the 3 on 2 minus 1280x plus 96000 square root x. Okay, so there we go. Or we could also rewrite it if you really wanted to, 4x to the 3 on 2 minus 1280x to the 2 on 2 plus, because 2 on 2 is still 1, 96000 x to the half. Okay, either way is fine, but there's our function for the volume. Restrict the function v of x to a viable or plausible domain. Okay, so what does it mean to be viable or plausible? Well, this equation is completely void of context. And what will happen if we actually go and graph this? Okay, let's go and graph it, edit, copy. Edit, paste. Okay, we want to graph. Okay, now I've graphed and nothing appears, and we've got to pay attention to the coefficients. We got a 4, we've got 1,280 and 96,000. So we've got some really big coefficients. So let's try and hit this button, which converts it to, and there we go. Okay, we've got something going on here, and it's hard to tell now. Our y-axis is really black. Now that button I just pressed, it tries to get key features of the graph, say turning points and that, to be visible. But we notice our y-axis is now a really thick black line, and that's because if we go into this, we can see our y-axis goes from negative 56,000 up to 333,000, and it's trying to put a scale on at every one, which is just not going to fit. So let's maybe put just a scale at 100,000 to start with. Okay, go OK. There we go. So now that's giving us a sense. Okay, as x goes up to the right, x, so an area, remembering that x is technically the area of the square, that's been cut out. This is what happens to the volume of the shape. Let's zoom out a bit more. Zoom out, zoom out. Okay, so we get this overall shape going on like so. And let's zoom out some more. Okay. We can keep scrolling across, scrolling across, scrolling across. We get this sort of situation. Okay. So I'm going to try and refine this a little bit more. Let's get it usable. I'll leave the negative there. Let's go out to 1,000 on the x. Let's go at intervals of 100. Okay. So I have that. And I can see this line still keeps going up and up and up and up and up and up. Okay. Let's, on the flip side, I can use this button here, and I'm going to... No, it's not worked. I'm going to zoom in on this area. I want to have a closer look what's going on here around the origin. There we go. Okay. Okay, so nothing to there, and this is what we want to do when we start graphing. We want to investigate. We need to zoom all the way out to get a large sense of the function, but then zoom back in and make sure we are not missing any key details. And no, it just looks like a regular square root. There's no little random jiggles or hidden surprises there. Okay, and our x value, okay, as I drag around, is very, very small. Our y values are still quite large. We can see that in the bottom left, okay, as I'm dragging it around. Okay, let's go back out, zoom out, zoom out. The thing is, so it just looks like a standard square root at the moment, but we want to go out further. So x min, x max, we were dealing with 1,000 before, and we can see that currently it's negative 3.1, but e to the negative 5, so that's saying times by 10 to the negative 5. So our x scale then got all the way down to like 0.003. So we can be pretty certain there was nothing funky going on. So x min, let's go negative 1,000, let's go x max, let's go all the way out to 10,000, scale of 1,000. Y min, well, we know our max is going to get up there, so let's go back up to 400,000. Okay. Rightio. Okay. Did I get that right? Yeah. Okay. X max is so we don't clearly need to go out that far. So let's go back to 2,000. Y max of and a thing that you can always do is just add more zeros. Okay, there we go. We're starting to see the curve. Let's add another 0. Ooh, there we go. Now we're starting to see the shape, and ooh, we actually notice it starts to go back down, go back down, go back down, and then crosses the x-axis, and we're getting a negative y value. Now we need to think about, what does the x represent? What does the x-axis, I guess, really represent? Okay, which is the, and in this case it's the area of cutout. Okay, and what does the y-axis represent? Well, it's the volume, and this is going to help us with what is a reasonable domain. Okay, now straight away, hopefully, because I've spent this long hunting around the graph to show you that, oh, it goes underneath the x-axis. That's an important fact. If the y value is negative, what's that saying? Well, the y-axis represents the volume of the box. That is trying to say that the volume's negative. Now, we're not allowed a negative volume. We can't have negative volumes. So straight away, wherever that point is, okay, where it crosses around, what's that, 15,000 for x, that's not allowed. We can't have an x value, so currently we know our x needs to be less than, and I'm going to put a squiggly in here to sort of say we're just estimating at the moment, that's about 15,000. And we'll come back and refine this in a smidge. Okay, it's about 15,000. On the flip side, let's go back to all the way to the start, and we'll notice that, oh, there's nothing when x is negative, but that also makes sense from a context of this problem. I can't have x be negative because I can't have a negative area cut out at the box. Am I somehow growing my cutout out here when x is negative? So clearly x must be greater than 0. I can't include it because if x is 0, well then that means we've got 0 cutout, which means we've got nothing to fold to actually get a box shaped volume. So to start with, as a very basic, we can have that as a somewhat logical domain. We can't have an area of the cutout be less than 0 or even 0. And it turns out that if our area of our cutout gets up above 15,000, well then the volume becomes 0 again. We need to do a little bit more thinking and maths from here, and this is a critical thinking of going from a function to what does the function apply to. What happens as x gets bigger? Well, as x gets bigger, our cutout gets bigger and bigger and bigger. And maybe you might see as I start to draw those, there is an issue. That's fine. As it's drawn is fine. Let's go red or brown. That's fine. But what happens if I get a little bit too big? And that's not very good. Let's use white. That's an issue. They start to overlap. So clearly the box can only ever get so big that we get to this situation. We need some sliver. We need some sliver width in here. And that, looking here, gives us a bit of a hint about what x can get up to. Okay. This width here has all the way across has a total of 240. And we're not carrying over this side because that's 400, it's wider. So really our cutout, because we have to have two of them, okay, the max width of that cutout can be up to but not including 120, because the midpoint here is at 120, so I can use up 120 over here and 120 over here. If both the cutouts are exactly 120 wide, well, the box ends up just getting cut off and I've got nothing in that midsection. If my width of the cutout is a little bit less than 120, well, I'm going to get this situation, which is completely fine. It's going to be a very, very narrow box, but it is technically completely fine. Okay. So from here, we can see that square root of x can be up to 120. Okay. So square root of x, okay, needs to be less than 120. From there, that means that x needs to be less than 120 squared. Ooh, why did I write an equal sign? Okay, x needs to be less than 120 squared, so x needs to be less than, if we do 120 squared, oh no, I'm in the wrong, 120 squared, oh look at that, it is 14400. It's near that roughly 15,000. Okay. So it turns out for x, okay, the area of the cutout is allowed to be between 0 or 14,400. That is our reasonable and acceptable domain. The first bit of that, the whole process, was looking at the graph, thinking about what does the x and y mean, and making some judgments from there. Then you need to come back and think of what was our first independent variable, which is our x, the area of the cutout. How does that impact the problem? Well, clearly I can't have a negative, and then if I start getting too big, those cutouts overlap, and that's why it actually is giving me that negative on the graph. So there is our reasonable domain. Our cutout can be anywhere between 0 or 14,400 centimeters squared, because it's technically an area. X is representing the area of the cutout. Okay, so we've done C. D is graph v of x, labeling all the key features. Okay, so we know from our graph before, we are going to be at 0, 0. So if we go back to the graphing window, I want, what am I doing? There we go. Okay. So we know it goes through 0, 0, and we also now know that it goes through 14,400, 0. They're going to be our key points. And looking at the graph, the maximum is sort of around 2,500. Okay, so that's actually quite low. So if that's 14, 10,000 is going to be about there, 5,000 is going to be there. So the maximum is about there. It goes up and down. Now, my graph hasn't actually had its maximum there. Let's get that a bit better. There we go. That's a bit better. You clearly want your maximum to be through that point. The last thing we want to do is we want to label that as a key point. What is that? Because here that's volume of x, and this axis is x. Okay. And this is in centimeters squared technically, and this is in centimeters cubed at the moment. What is that maximum volume? Well, we can use our analysts and we can find our max, and there we go. Using analyst GSolve, we hit max. It's given us our max is 2356.9, comma, and it says 2.1 E, and looking at this little bit in here, 2.1 E plus 6, so that's 2.1 times 10 to the 6, but if we look down the bottom right, it actually tells us what the y coordinate is. It says XC, which means x coordinate, and then YC, which is y coordinate. And we can see actually in the x coordinate is 0.9099, so if we wanted to round to 2 decimal places, that's technically having it 2.91. And then the y coordinate is 2,100, 0.1458.1. Okay. So, sense of scale, that is 2.1 million. Am I reading that right? 2101458. Yeah, 2.1 million cubic centimeters. So that's what our graph would have to be. Of course, straight rule axes. Identify what x will be when the volume is maximized and what the dimensions of the cutout itself are. Okay, so we've found, okay, x is 2.10, and just for rounding sake, no, let's actually write it all the way out. X is equal to 2101458.1 centimeters cubed. Now the dimensions of the cutout, so that's the area. And that's our area. So that means in there, and it's a square cutout, 2.1 by 10 to the 6. We want to find our length, in which we know from before is square root of x. So square root of x is, oh no, I've made an error. No, that's what I was writing. It's just my issue. Let's undo. Okay. The volume was that, which is the volume. Now, I need to go back to the question. I've got myself in a muddle. Identify what X will be when the volume is maximized and what the dimensions of the cutout itself is. Okay. So the volume is that. X is, silly me, is that bit there. Okay, so the area of the cutout, okay, area is 2356.91. 2356.91, which is the right number because it's got to be less than what we figured out before was the maximal. Okay. There should be zero there. So square root of x, okay, is square root of x is equal to the square root of 2356.91, which if we go back to main, square root 2356.91, decimal, I want it, is 48.54801. So it is roughly equal to, let's go 2 decimal places for the lack, because that's what it's consistently been so far, 48.55 centimeters. Okay, so the length and width are both roughly equal to 48.55 centimeters. And in a worded SAC like this, you'd want to write that as a sentence. Okay, but then it says, write a statement answering the questions Molly first posed. So that is up here. Those are the questions here that she first posed. So you need to write out a full statement. It would probably be a paragraph, maybe even more. Okay. What is the range of possible volumes? You need to state that, the range of possible. The maximum possible volume is blah. What are the final dimensions? Well, the final dimensions, okay, are cutouts, and this is important. At no stage have we actually found, okay, how much aluminium would be wasted as a percentage of the original area of the sheet if made to maximize volume. So we still need to do some maths. Okay, so we need to do some stuff around percentages. Well, the area of the whole sheet was originally 400 by 240. 400 by 240. Okay, so is 96000. Okay. The area of the cutout, because there was 4 of them, is 4 times by, and we said the cutout was 2356.91. Okay. 4 by 2356.91 is 9427.64. So the percentage of material wastage, the wastage is going to be equal to 9427.64 divided by 96000, which we can already see is it's going to be a little bit under 10%. Times all that by 100, fraction. Okay, equals 9.82%. Okay, so that was the last little bit of maths you need to actually do to write a statement answering all the questions that Molly actually asked. So this is where we need to make sure we're reading the prompts and questions properly. But that's it on component 2.